Hi everyone. In this video, we're going to talk about section 3.6, which is about the Poisson distribution. Okay, so the Poisson distribution is the last sort of discrete distribution that we're going to talk about for chapter 3, and then we're going to move on to chapter 4, which involves continuous probability distributions. So let's talk about the Poisson distribution. All right. So unlike the other distributions that we've seen so far, the binomial, negative binomial, and hypergeometric, the Poisson distribution doesn't originate from a simple experiment. So my random variable is not always going to be counting the number of successes out of n trials, or counting the number of trials or failures until the rth success, or so on and so forth. Okay, like we saw before, it can be a variety of different things, and so we sort of can't define that experiment before we see it. And then afterwards, after we look at the experiment, we can say, does this fit a Poisson distribution or not? Anyway, you may look at that. This is Poisson is the French word for fish, I believe. Okay, and it's after a French statistician or mathematician who made this sort of up. So this is his name, his last name. A lot of people pronounce it Poisson. So you can either say Poisson, or if you want to say it more in a French accent, or pronounce it how the French would pronounce it, it's Poisson. Okay. Anyway, it doesn't really matter. It's most often used for counting the number of events that happen in a fixed interval of time or space. And so it is counting things usually, and it might be standing in a shop and counting the number of people who come in for 5 minutes, and we're interested ultimately, or what makes the Poisson distribution it's like its own self is going to be the rate at which people come in. So that's really what makes it go. But ultimately, the random variable that we're looking at in this case would be that count, the actual count. Okay, so the Poisson distribution has one parameter, and that parameter I'm going to call lambda. Okay, I'm going to call it lambda. The book calls it mu. And so keep in mind that when they talk about the Poisson distribution, I'm going to use lambda. They're going to use mu. I'm sorry to keep changing from what the book says, but if you look anywhere else for the Poisson distribution, you're going to find a rate parameter of lambda. Okay, and so that rate could be a many number of things. If we're counting events that happen in a fixed interval of time or space, that rate parameter could be the mean number. It's usually it's a mean, we'll find out, but it could be like the rate of people that come in per minute or per hour or over a fixed space interval. And so that's the rate at which people, places, things, so on and so forth do whatever that the question is interested in. That's sort of what makes the Poisson distribution distinct from everything else. So rate parameter. We would denote it if x does have a Poisson distribution. We have the tilde there, and then POIS is the prefix sort of that we use, and then the one parameter that we have is lambda. Great. And so here's the PMF. The PMF only involves x and lambda, and the PMF is pretty simple. E raised to the negative lambda times lambda to the x divided by x factorial. And x here can be a non-negative integer. So it could be 0, 1, 2, 3, all the way up to possibly infinity. Okay. And so that is the Poisson distribution. So let's see what a question that uses it looks like. So if I have a random variable x and it denotes the number of traps which is defects of a certain kind in a particular type of metal oxide semiconductor transistor. Okay, suppose it has a Poisson distribution with lambda equal 2. Okay, so the rate over a certain interval of time or space where they're looking at these transistors, the rate of defects, the rate of traps is 2 over some set interval of time. Okay, and we're saying that X has that Poisson distribution with that rate lambda. And so I asked the following questions. I'm going to ask a PMF question and a CDF question. What's the probability that there are exactly 3 traps? Okay, and so we are finding the probability that X, which has a Poisson distribution up here, it says in the problem, so we don't really need to write it down. The probability that X is equal to 3, okay, and then we're going to use this lambda, and the PMF is e raised to the negative lambda, so e raised to the negative 2 power, lambda to the x, so 2 to the 3rd power over x factorial, which is 3 factorial. Okay, so we know some of these things. 2 cubed is 8, okay, and 3 factorial is 3 times 2 times 1, which is 6. So we've got 8e to the negative 2 over 6, and we can pull out a 2 for each, and so we have 4e to the negative 2 over 3. Okay, and so if you do some quick calculations here, let me just pull up a calculator for a second. You can do the calculations as I'm trying to do here. Okay, so when I did the calculations, just quickly off my calculator, I got that this is 0.18 around that. And so it keeps on going, but I'll round it off at 2. It's 0.447, so on and so forth. Okay, but really we don't need those. We'll just go to 0.18. Okay, so great. That's the probability that there are exactly 3 traps when I perform my experiment, right? Then, next one, what's the probability that there are at most 3? At most 3. And actually, after we're done this, we'll go to Minitab, and Minitab can redo these calculations and make sure that we're correct. Okay? At most 3. And so that is the probability that x is less than or equal to 3. So 0, and so what could be possible? Well, I could have 0 defects, 1, 2, or 3. And so that would be x equals 0 plus x equals 1 plus x equals 2 plus x equals 3. Okay, and of course, that's not too terrible to do. The PDF is just e to the negative lambda, lambda to the x over x factorial. Okay, and so then you can plug in the numbers. You can substitute those numbers in. And so you'd have something like, if we came down here, that would be e to the negative lambda lambda to the 0th power over 0 factorial. Anything to the 0th power is 1, and 0 factorial is also 1. So 0 is easy. It's just e to the negative 2 plus, and then so on and so forth. Okay, but I'm not going to do that here. We're just going to let Minitab do that for us. So I'm now going to switch quickly from our presentation here, Minitab, okay, and I want to go to Calculate, Probability Distributions, Cumulative Probability. Again, this is a Mac. If you have a PC, it's slightly different. Okay. And I'm still inputting a single value, and my value is 3. But now I'm choosing a Poisson distribution, which is right below the normal, which is where you usually start. And the mean, or the rate parameter, is 2. Okay, so this would be the answer to the second part. Calculate. The answer to the second part here, if we blow this up a little bit, is 0.857. Okay, and so that's going to be the answer to that second question. Now, if we wanted to check our first question, we could do this again, just with probability density. We found exactly 3 the first time. And we got 0.180447. Okay, which is what I calculated by hand. So everything worked out, thank goodness. And so I want you to do your turn. Okay, so I give you an example here, and I ask you a PMF question and a CDF question. Okay. X equals 1, and then at most 3. All right, so hopefully that won't be too bad. Now, just as an ending here, the Poisson distribution, and I'll have to go back actually at the end of this video and tack on the negative binomial because I forgot this, but the Poisson distribution has its own mean and standard deviation like we found for the rest of the distribution. So if X is a Poisson with mean or rate lambda, it turns out that the mean of that distribution is lambda and the variance of that distribution is lambda. And that's pretty weird because that's not true for most things. The mean and the variance are usually not equal. And so, but the Poisson distribution has that sort of property. Okay? We'll come back to the Poisson distribution because we're going to talk about a thing called a Poisson process when we get to the stochastic part of this course. And so we'll see that in just a little while. And then the last bit here, the negative binomial distribution, which I forgot to mention, also has a mean and a variance. And here they are. So if you remember, the negative binomial distribution was the Rth success and the probability of success P. Okay, and so those are our two parameters, and the mean and the variance are functions of those two. The mean is R times 1 minus P over P, and then the variance is the same thing on the top and P squared on the bottom. Okay, and so that's it for chapter 3 of what I want to do with it. And so next time we're going to move on to chapter 4.